Good afternoon, everyone. I'm Sourab Mangrulkar, machine learning engineer at Hugging Face.
Hi everyone, my name is Younes, and same as Sourab, I'm also a machine learning engineer at Hugging Face, and I'm super excited to be here and present you with my colleague how to train LLaMA in your backyard.
Great. So today we'll be presenting the talk titled Training a Llama in Your Backyard, wherein we'll be looking how to fine-tune very large models on consumer hardware using Hugging Face transformers and Hugging Face parameter-efficient fine-tuning libraries. Let's get started. So first, we'll look at what makes a model large and why fine-tuning becomes expensive as model gets larger and larger. The size of the model, the memory required to load the model depends on two things: the number of parameters of the model and the precision in which you are loading it. For this, we'll take LLaMA 7 billion parameters model as an example. Here, if we load the model in full precision, that is float 32, the memory required per billion parameters is 4 GB. So in total, we require 7 into 4, that is 28 GB, to just load the model in full precision. Now, if we load the same LLaMA 7 billion parameter model using half precision, that is in float 16 or brain float 16, the memory required per billion parameters is 2 GB. That is, in total, we require 14 GB, which is half of what we required when compared to full precision. Now, let's look at why fine-tuning LLaMA 7B large language model is a bit expensive, right? So for that, the memory cost per parameter, here we will be considering full fine-tuning with mixed precision using RM optimizer. Here, the memory cost for weight is 2 bytes because they are in half precision. Same goes for gradients. Because they are in half precision, they will take 2 bytes per parameter. For optimizer states, when using RM, we keep a copy of the original model in full precision, which takes 4 bytes per parameter. And the momentum and variance estimates again take 4 bytes per parameter because they too are in full precision. So in total, we require 16 bytes per parameter. And because the model has 7 billion parameters, this becomes 7 into 16, that is 112 GB. This is not even considering the memory required for intermediate activations. We can see that more than 100 GB of memory requirement. For this, we'll require at least 440 GB GPUs or 280 GB GPUs, which is quite inaccessible compared, like when we take into consideration that most consumer GPUs have like GPU memory ranging from 8 GB to 24 GB.
Yeah, so now that we have pretty much understood what would be the cost for loading the LLaMA model and to train, to fine-tune the LLaMA model, let's try to understand altogether why do we need PEFT methods and what is the core question that PEFT methods try to answer today. So I think today, in order to fine-tune LLMs, there are different there are different levels of skills and knowledge that users need to face. So obviously, we'll start with the level 1. Where we would do all the experiments in a single GPU setup. And note that in this case, it's totally possible to run your experiment on free-tier instances, such as Google Colab or Kaggle notebooks. Then suddenly, you have access to more GPUs, so you come to level 2 and start performing multi-GPU training. In that case, you might be interested to use torch distributed or some modules such as distributed data parallel. Then I think this is really where exactly comes the large-scale barrier. Whenever you want to scale up the experiments and fine-tune larger models, then you would need a larger infrastructure and larger costs. And comes level 3, where you would scale up the experiments on a single node training. So in that case, you would definitely need to have access to a cluster of GPU, for example. Then you would need to run the experiments on Slurm, maybe manipulate some of the a little bit complex paradigms for end users, such as DP and PP. And then ultimately, there is the level 4, the extreme scale level, where you can fine-tune any model that you want on a multi-node setup, for example. You can perform DP, TP, and PP without any issue. And yeah, note that in the two big levels, obviously the scales of models that you can fine-tune is completely different. In the first case, you can maybe only fine-tune up to 1 billion scale parameter models, which gives you which doesn't give you access to the state-of-the-art LLMs, obviously. Whereas on the right hand, I think there is no limit. You can probably fine-tune up to 100B scale models, which give you access to all the state-of-the-art models, such as LLaMA 7B, 70B, and so on. And one interesting thing to notice here is that on the right side, you'll definitely need, in most of the time, obviously, to manipulate some advanced open source tools that can be a little bit complex for some end users. Whereas on the left side, you can do literally everything in pure PyTorch. And this is much better in terms of accessibility for the community. And I think the core question that PEF tries to answer today is, can we break this barrier and be able to train large-scale models using simple approaches and tools? And also, can we use the resources that you can see on the left in order to fine-tune the models that are only accessible on the right? So we'll see that this is totally possible using PEF methods. So PEF stands for parameter efficient fine-tuning. And today we can count various types of PEF methods. So there are several PEF methods that are known today. So this is a figure from the paper that you can see here. And for the talk today, we're going to focus on LoRa, which stands for low rank adaptation, because they're the most popular one today and the most adopted by the community. So let's have a deep dive into low rank adaptation LoRa with Hugging Face's PEF library. So you can see on the left the figure of the low rank adaptation method. So in a nutshell, you just have to attach some external trainable parameters on top of frozen weights that are in blue. And the trainable parameters have this autoencoder style shape where the R parameter is usually very small compared to the dimensionality of the hidden states, which makes those two matrices, trainable matrices A and B, very sparse compared to the blue matrix. And in terms of user experience, as you can see on the right, so how does it look like today? So first of all, you need to import all the relevant modules using transformers and PEF, so auto-model for causal LM, and from PEF we're going to import the LoRa config to define our LoRa modules. And obviously, yes, load your model. Here we'll load it in float 16. Then we'll define the LoRa config. We will define also the R parameter. As you can see here, it's pretty much small. So here we use 8. And we also define the task type, which is causal LM. And then we just need to call model.addAdapter LoRa config to attach the adapters. And then, yeah, you can basically train your model, do whatever you want. And finally, model.save pre-trained your path to the adapter model. And the cool thing to notice here is that when you save your adapter weights, you only save basically the adapter weights, so not the entire model. So for LLaMA 7B, if you use the basic configuration, you just end up saving 300 megabytes instead of saving the whole model, which is great for distribution. So let's do some quick calculation on how much would it cost in terms of training. So there is a cool utility method in PEF where you can print the number of trainable parameters once you have attached the adapters to the model. So here in this case, we end up by having only 0.29% of trainable parameters. And yeah, same as before, the weights stay untouched of 14 gigabytes. Same for the gradients. As Sourab explained before, same for the optimizer states. But here we'll multiply the 112 by 0.0029 plus the 14 gigabytes for the model weights, which ends up by having only 14.3 gigabytes for fine-tuning LLaMA 7B in float 16, which is great because beforehand, for full fine-tuning, we were around 112 gigabytes, and now we're only we basically only need approximately 14 gigabytes, and yeah, this is great, and yeah, opens up a lot of opportunity for end users. But can we go further? Can we reduce this parameter further and probably reduce the memory requirement for the training setup. And we'll see that this is possible by compressing the base model by leveraging quantization.
Yeah, so now we'll look at how we can use quantization to further decrease the memory requirements for training or tuning the LLaMA 7B model. So this is the diagram explaining how low-rank adaptation PEF method works, wherein the pre-trained weights are in blue and the trainable low-rank matrices are in orange. So now we'll be focusing on how we can use quantization to reduce the memory requirements for the pre-trained base model weights, which are highlighted in like blue here. Before that, let's go through an example to understand how quantization works. Then we'll look at QLoRa, which combines LoRa with quantization, and see how to use it in terms of user experience. Here, quantization in broad sense is mapping a continuous signal into discrete domain. In this case, we are taking the example of 4-bit quantization. On the right-hand side, there is a mapping from indices 0 to 15 to their corresponding values. These 16 indices are the 16 quantities that can be represented using 4 bits because 2 power 4 is 16. And then we have, for example, a weight vector in half precision, floating point 16 on the left-hand side here. The first step to do quantization is to find the absolute maximum and then divide the whole vector by it. In this case, it is 10. So once we divide by the absolute maximum, we get the normalized half precision vector. So the next step is to do the index lookup. For example, the closest value to 0.13 is 0.11, and the corresponding index value is 8. We do this for rest of the entries, and this gives us the quantized 4-bit vector. Here, we can see that each of the entries can be represented using 4 bits. For example, 8 can be represented in binary as 1000, which requires just 4 bits. Now, for forward and backward passes, we need to dequantize this quantized 4-bit vector to compute. Let's see how to do that. The first step is to do the reverse index lookup. We can see at index 8, the value is 0.11, and we do the same thing for rest of the entries. The next step is to multiply again by the absolute maximum. This gives us the dequantized half precision vector. Notice that there are differences, a bit of a difference between the original vector and the dequantized vector. For example, 1.3 became 1.1, 5.1 became 4.6, minus 3.5 became minus 3.3. This is what is known as quantization error, and the quantization techniques do their best to minimize or avoid this quantization error, because larger quantization errors would lead to performance degradation. Now, let's look at QLoRa. In QLoRa, they combine LoRa with quantization, wherein the base pre-trained model weights are quantized using 4-bit quantization with normal float 4 data type. Now, let's see how to use it. As Younes explained earlier, we'll import auto model from transformers and LoRa config from PEF. Now, while we load the pre-trained model using from pre-trained method, notice that we are passing a new flag, load in 4-bit, which we are setting to true. This loads the base pre-trained model in quantized format, wherein they are stored using 4 bits. Next, we create the LoRa config, and then we add the adapter or insert the LoRa layers using the LoRa config. That's it. So this enables anyone to use QLoRa, and like it is super convenient, and you train it as usual, and then save the adaptive weights. Now let's look at how much memory we are saving by using QLoRa. The memory cost per parameter for weights here would be half a byte because we are using 4 bits. So for 7 billion parameters, it's approximately 4 GB. The gradients and optimizer states are as before, but because we only have 0.29% trainable parameters, the 112 GB we multiply first with the number of trainable parameters or percentage of trainable parameters, that is 0.0029, plus we add the base model memory requirements in 4 bits, that is approximately 4 GB, which gives us approximately 4.5 GB. So we can see that we have reduced the memory requirements for full fine-tuning, which required 112 GB to 14 GB with just using LoRa, and then to 4.5 GB using QLoRa. And that's how you can train a LLaMA in your own backyard using, just 16 GB or 12 GB GPUs, and you can obviously do it on free tier Google Colab GPU.
So yeah, all of this is super cool. We can now fine-tune your own LLaMA on your own backyard. I think this is great because, for example, 2 years ago, it was not even possible to run inference of a T5 model on a Google Colab. Now it's possible to fine-tune a LLaMA model on Google Colab. So yeah, all of this is really good. So, OK, we've just discussed that it's possible to fine-tune your model on a Google Colab, but how does this affect the model's performance? Is there any performance degradation on the model? Let's see that very quickly on the next slides. So, as mentioned on the keynotes before, so we had a look on this OpenLLM leaderboard from Hugging Face as of the 20th of September 2023. And as you can see here, at least 3 models are based on LoRa, and one of them is based on QLoRa, so the one on the top. So yeah, this simply attests that LoRa and QLoRa can perform as good as models that has been fully fine-tuned using other frameworks. So yeah, all of this proves that yeah, there is no performance degradation if you want to fine-tune your LLaMA model or any language model using LoRa or QLoRa. And it is really used in practice, as you can see here. So you have some of the top models of the OpenLLM leaderboard uses LoRa or QLoRa. So yeah, before wrapping up the presentation, we wanted to have some cool examples and applications on what you can do by fine-tuning LLaMA 7B for your use case, for example. So the first use case that we wanted to show you today is PEFT applied to RLHF. So RLHF is an exciting topic because we know that OpenAI uses RLHF to fine-tune ChatGPT. So we proved that we've proved that it's possible to perform RLHF using PEFT. So there is a team at Hugging Face that used this library called Transformers Reinforcement Learning from Hugging Face to fine-tune LLaMA B using the so-called DPO algorithm, which is an RLHF algorithm. And yeah, the produced model is called StackLaMA because it has been fine-tuned on some preference data set of Stack Overflow. And yeah, you can read more about it in this blog post. We also exposed a Google Colab notebook on fine-tuning LLaMA 2.7b chat for generating some short text advertising. So to give an example, so we give here to the model to generate some advertising around the PS5 from Sony. So as you can see before fine-tuning, the model somehow, I would say, hallucinate a bit, generates a lot of text. The advertising is not really consistent. Whereas after fine-tuning, the advertising is much more consistent. It's much more compact as well, and even in terms of content, it's pretty nice. So yeah, we exposed this notebook, and we also share a link on the last slide for anyone that is interested to reproduce this experiment. Another cool example that can be applied in many use cases is to fine-tune code LLaMA on some proprietary code base. So if you have, for example, a private database and you want to fine-tune a code assistant on this database, you can do it using CodeLaMA, for example, and PEFT. So we try to do it by fine-tuning CodeLaMA into the PEFT library itself. So if you prompt this, this beginning of a code snippet before fine-tuning, as you can see, it produces some code, but it's not really consistent with the PEFT API, and this code actually doesn't work if you run it with PEFT. Whereas after fine-tuning, it gets the perfect API, and yeah, you can run this API also out of the box using PEFT. So yeah, this is really cool as well. Another application that we wanted to highlight is the fine-tuning idFX model. So idFX is a model that has been released by Hugging Face, which is a multimodal model that takes text and image and generates some text on top of it. So the cool thing with LoRa is that it's also modality agnostic, meaning that you can also apply to image models, you can also apply to multimodal models, you can also apply to audio models. And we also expose this Colab notebook where you can fine-tune idFX 9b to generate some description given some Pokemon cards. So if we ask this question to idFX 9b before fine-tuning, it generates some text, which is more or less accurate, but still the text is not really consistent and not really compact. Whereas after fine-tuning, the text is much better, and we believe that with further fine-tuning and better dataset quality, it might be able to get the accurate information of the Pokemon cards. Yeah, so that was it pretty much for today. Before ending up the presentation, we wanted to acknowledge some of the contributors that really helped building this app all together. So we wanted to thank, first of all, the Microsoft team for open sourcing the LoRa code. We also wanted to thank the researchers from University of Washington for their work on QLoRa. We also wanted to thank the Bits and Bytes maintainers and contributors, and probably many other people that we forgot to mention today that helped building this ML community for the contribution, help, and feedback. And this is the last slide with all the useful links for today. So if you want to reproduce the experiments that we made for the presentation today, you can maybe just take a picture or download the slides later offline, where we stored all the notebooks and everything to reproduce the experiments. Thank you very much.